All right. So by now, you have hopefully watched all four of those three blue, one brown videos. I believe it's four of them. Yeah. If you haven't, you should pause right now, watch them. I include them in the link underneath again. So please, if you haven't, go and watch them. All right. All right. Cool. So now we're going to do two things today. First of all, we're going to go back to that sunny, rainy problem and solve it for the long run behavior, not just for the long run, but at all points in time. We're going to solve that. And secondly, what we're going to do by using all the matrix stuff that you hopefully learned in those videos. And secondly, we're going to go back and do some stuff with specifically absorbing Markov chains, which is what you saw back with the chutes and ladders, where in an absorbing Markov chain, you're going between states, but you eventually stop transitioning. You end up at some place where you get stuck. And that's an absorbing state in the Markov chain. And in this case, it was the end state in chutes and ladders, right? Because once you reach the end, you no longer move anywhere and you just stay there. Now, it turns out that when you have more interesting Markov chains, absorbing Markov chains, you might have multiple endpoints, multiple absorbing states. So, for example, one that you can imagine, and this is kind of a cool variant, is if you have chutes and ladders, right? You have chutes, and then you have your ladders. You got your start, you got your end here, right? And then what I like to do is I think of a different variant on it. You know, here's your ladders, right? And then you maybe have a chute. Woo. Right? I think, I probably send them back to like the start at some point with one of the chutes. Well, what you can also do is you can add in chutes, ladders, and like the shadow realm, right? Which I can't really draw that, I don't know, like some skull and crossbones or something, right? Where you die, right? Chutes, ladders, and hell and death, right? Shadow realm. And so what happens is that if you land on this square, you're goner, game over. And if you end here, you also stop here. And so here you have two different absorbing states. And a question that you might ask is, well, what percentage of the time do I end up in the shadow realm? What percentage of the time do I actually reach the end? Right? So those are two different absorbing states, and you have to figure out what the probability is of each. And now how you do that is you could run it via Monte Carlo simulations, right? You can start off here and start rolling and simulate it a million times and see on average. But we'd actually like to try to solve it analytically. And so that's something that we'll also do today. Get some equations for doing this. All right. So back to the old sunny rainy, right? We end up with this matrix 0.9, 0.5, 0. I'm sorry, 0.1, 0.5, 0.5, and then you can multiply by some x and y, and then you get the next period's x and y, right? N plus 1, y, n plus 1. Now, now what we're going to do, though, is I believe pretty much in all of the videos that you're watching, traditionally, what we're doing in the 3 blue, 1 brown, the way that they did the matrices, and it's kind of unfortunate that standard Markov matrices are written like this, but in all other math that you do, you always you typically want to multiply by the column vector is the traditional thing, and so all the stuff with eigenvector and stuff traditionally is written with the eigenvector like this, where it's a times v is equal to lambda v, right? Where this is saying you take a matrix, you multiply it by the vector, and you get the same vector back, just scaled, right? And so traditionally, you would write that as a column vector rather than the row vector like this. So for the rest of the class right here, for doing this analysis, I'm gonna flip it back around like we had it at the very beginning of where we had it when I first introduced it a little bit. So let me flip it around here. And we have, what is it? It was 0.9, 0.5, 0.1, 0.5 times xy gives us x n plus 1 right? That's what we have. And so now what we want to do is figure out, okay, got it. There we go. All right. Sorry, that was starting to fall out a bit. All right. So what we want to do, though, is ultimately the problem that we had left off with was that we wanted to figure out what is this matrix to the nth power. And the reason why is because then if we have our initial states, we can get the nth state. But unfortunately, taking this thing to the nth power is not a trivial task. And it turns out what we're going to be needing is the eigenvectors and eigenvalues. So let's quickly do that. We'll find the eigenvector and eigenvalues of this matrix. And it turns out it actually has some clear, it has to have certain things to be the case. And then once we solve it, we'll talk about some of those properties, and then we'll actually take this and figure out how to take this thing to the nth power. All right? So let's go to it. So first, hopefully from the videos, you learned that this means that the determinant of a minus lambda I has to be equal to 0. And so therefore we have 0.9 minus lambda, 0.5, 0.1, 0.5 minus lambda. Determinant has to be equal to 0. And therefore, we're going to get that. Oh boy, we got to multiply this out. So we get 0.45 lambda. This probably would be easier if let me convert these just to, instead of having them be decimals, let's do fractions just for simplicity's sake. 1/10, 1/2, and 1/2. That'll probably make the math a little bit easier for me. All right. So let's see here. So we got to multiply 9/10 minus lambda times 1/2 minus lambda, and then we have to say minus 1/20, right? Or 1/10 times 1/2, which I'll write out. 1/10, 1/2. And that whole thing has to be equal to 0. And so let's do that. We get 9/20. Let's see here. Minus 9/10 lambda, minus 1/2 lambda, which is going to be minus 14/10 lambda. Is that right? Pretty sure that's right. Plus lambda squared. And this is a minus 1/20. Has to be equal to 0. And so we should get 8/20 minus 14/10 lambda plus lambda squared is equal to 0. Luckily, this one we can actually factor it. I know already that because I already know that that minus 1, that 1 should be a solution. Give me just 1 second here. Have I hope I didn't mess anything up. I guess we'll find out in a moment. It's all right. Let's see here. I believe that we should be able to get that x, that, let's see here. Lambda minus 1. I believe that this is supposed to be a solution. Let me see here. So 8/20. We'll see. I'm about to figure out if I made a mistake, so don't spoil it for me. This should be 0.4. If we write it out maybe in decimals, maybe it'll go back to being easy again. And this one is a minus 1.4. So that should be pretty clear, right? Times lambda, and then that is going to be minus 0.4. Does that work? Let's see here. Minus 0.1 times minus 0.4 is 0.4. Minus 1 lambda, minus 0.4 lambda, minus 1.4 lambda. That works out just fine. So alternatively, I could have written 1. Yeah, I'm just curious here. Let me see here. 1 plus that thing is minus 4/10. Yeah, perfect. Yeah, perfect. All right. There we go. So we get this, so therefore lambda is equal to 0.4 or 1. All right, perfect. So those are our two eigenvalues. Now we're going to have to plug them back in and get our eigenvectors. All right, so what we know, if we go back here, is that our matrix 0.9, 0.5, 0.1, 0.5 times by our eigenvector, which we'll just label xy, has to be equal to, we'll first do the one with lambda equals 1. Right? So therefore it just has to equal 1 times the vector itself. Right? Easy. So this one comes out to be that, and these are always going to end up not being able to actually get solved fully. Right? 0 plus 0.5 y has to equal x. Right? Just multiplying this through. And then also that 0.1x plus 0.5y has to equal y. Once again, I believe we saw this last time where this thing couldn't easily get solved, right? Unless we put in the constraint that x plus y has to equal 1, which is a pretty reasonable assumption here, but actually is not necessary here. In general, what we're going to get out of this is that 5y is equal to x. So in general, what we can do is that what you do is that because any vector, all that cares about for the eigenvector is the direction. We've gotten that from the videos. We can actually choose any vector we want as long as it's in that direction. So as long as x is equal to 5 times y, you can put it anywhere you want. All right, you can have it be any length it wants. So for this first one, traditionally what people choose is either something that sums up to 1, something of length 1 is the most common. So that would mean x squared plus y squared is 1. In my case, I'm just going to choose something nice and easy here. If y is 1, x should be 5y, so that's going to be 5. All right. So this is going to be our v1 here, and we'll label this one lambda 1. Now we got to do the same thing for lambda 2. All right. And in this case, what we have, I probably shouldn't have erased everything. Let me just move this over here. Lambda 1 equals 1. Lambda v1 equals 5, 1. And then we can say that 0 0.9, 0 0.5, 0 0.1, 0 0.5, v2 has to be equal to 0 0.4 or 2/5 v2, right? Or, xy, xy. Right? And so here we're going to get more or less the same thing, except now instead of having 0.9x plus 0.95y is equal to x, it's now going to be 0.4x on the other side. And once again, you're going to get the same thing on the bottom there. It doesn't really matter, those things. What you're going to end up getting is that 0.9x plus 0.5y. These two will always be, by definition, because it's an eigenvector specifically, these two will always be linearly dependent. So you can never actually get the solution, you only get the direction. Right? And so this is equal to 0.4x. Subtract off, let's move it to that side, and we get 0.5y is equal to minus 0.5x. Therefore, y is equal to minus x. So what we can do is that we can say lambda 2 is equal to 0.4, and v2 is equal to, we'll just choose 1 minus 1. Something nice and easy. All right, so there we go. We've solved for our eigenvalues and eigenvector. And it's kind of interesting. All right, and we'll see why in a minute. We'll first do one last step here, which is how do you now take this matrix to the nth power, right? That's what we want to know. And that's the big question. And it's not too hard to do, because what we know is, once again, 0 0.5, 0 0.1, 0 0.5. We know that if we multiply by one of the two eigenvectors, all we're going to do is just scale it. and stay in the same direction. But unfortunately, we don't have one of the eigenvectors. We have whatever x0, y0 are. Right? And unless we happen to get very lucky and start in the direction of an eigenvector, we're going to be out of luck, right? Not so fast. We can do a little trick here. The trick is very simple. We can say that x0, y0 is equal to, some say, alpha times our vector, our first eigenvector, plus beta times our second eigenvector. So what we can do is we can decompose it into some component of our first eigenvector and our second eigenvector. So all we have to do is just figure out some linear combination of the two that equal it. So in our case, I believe we started with it being for sure sunny, right? And you'll see once we split it up, it makes the multiplication very straightforward. So for example here, if we start off being sunny, right, then we have alpha 5, 1, and we could solve this in general, but we'll actually solve it specifically for real fast, right? Since we have this, that just means that 1 equals 5 alpha plus beta, and then 0 is equal to alpha minus beta. So in this case, luckily, alpha must equal beta. According to this equation, we plug that in. So therefore, 5 alpha plus alpha equals 1. So that means alpha equals 1/6, and beta also equals 1/6. Let's just double check here. So we get 1/6 minus 1/6, that's 0, right? That checks out. And then 5/6 plus 1/6, that's 1. Cool. So now what we have is that what we really want to do is we want to take our 0.9, 0.5, 0.5, 0.1, and then we want to take this to the nth power. So we want to multiply this vector n times, so that way we get xn, yn, right? Xn, yn. But what it says, we can split it up like this. So let's do that. This is where we get some cool stuff, right? So we get 1/6 times 5, 1 plus 1/6 times 1 minus 1. Right? And don't worry, we're actually going to visualize this in just a minute. It's going to be really cool. I have a nice little computer program to show you this. All right. So we have this. And now we can just pull out the 1/6 if we want. So this is equal to 1/6 times, now it's just going to be this 0.9, 0.5, 0.1, 0.5 to the n times 5, 1 plus 0.9, 0.5, no, that's all right, and then 0.5 times 1 minus 1, all right, to the n. So that's all we got to do. And luckily, this multiplication is easy. Because if we multiply this matrix by the eigenvector once, all we do is we get the same value back because the eigenvalue is 1. And so what this thing turns into is just 1/6 times lambda 1 to the n, which in this case, lambda 1 was 1, times our eigenvector, plus lambda 2 to the n times second eigenvector. Cool. And there we go. So now what we've done is that since this is 1 and this is 0.4, we just take them to the nth power and we're good to go. Let's take a look at it. What happens when we run it for a lot of periods? This is where it gets pretty cool, right? So what we have is that we know that x n y n must be equal to just 5, 1. That's just fixed. Sorry, 1/6. So we'll say 5/6, 1/6. We'll finally divide through that by that 6. And that's just 1 to the n, right? plus right here, we get our 0.4 to the n times 1 minus 1. And what happens as we go off towards infinity, as we go larger and larger n? Well, this number right here, 0.4 to the n, gets smaller and smaller. It depletes, and it eventually goes to 0. And what we're going to end up with, this one with the 1 stays put, and we get 5, 6, 1, 6. So whenever a Markov chain converges, what we can see here is that all the that what you will always have in a regular Markov chain that actually converges is that you will have one of the eigenvalues has to be 1, because as you run it off to infinity, if you have any eigenvector greater than 1, eventually that term will blow up, and so therefore your vector will go off towards infinity. And we can't have that, because if the vector went off towards infinity, then clearly your total probability is going above 1. Likewise, if they're all less than 1, then you'd eventually go down to the state 0, 0, and you'd be 0 probability of being anywhere, which that also isn't valid. So what you end up having when it converges is one of them, and all regular Markov chains do, one of them will have an eigenvalue of 1, and that corresponding eigenvector is what it converges to. And then all the other ones will have either positive or negative eigenvalues, but they're all going to have an absolute value of less than 1. And so they decay off to 0 with time, and you're going to end up with just this. All right, just your primary eigenvector. So let's actually quickly see this on the board, on the computer, I mean. So I have this little Mathematica thing. I haven't ever bothered to remake it in Python, although I should. So I have this 0.9, let me zoom in a little bit here for you. So I have this 0.9, 0.1, 0.5, 0.5 matrix. And then I give it the initial starting point of sunny, so that's 1, 0. And then we're going to run it for 20 times. And what you can see on the left here, I have two graphs. The left here shows the current location, right? 1, 0. Probability of sunny, probability of rainy. And if I push it forward one step, you'll see it goes to 0.9, 0.1. And right here, I just have the time series showing probability of sunny going from 1 down to 0.9, and then 0 up to 0.1 for rainy. And if you run it forward a second period, third, fourth, fifth, and then eventually it converges to our 5, 6, 1, 6. You can just play it. It's just a nice little animation. Easy. Now, what I have here is I can show the eigenvectors. And now this is it composed, right? So here is our 1, 6 in the direction of 5, 1. And right here is our minus 1, 1, or 1 minus 1, right? You can see the slope here is plus 1 minus 1, which corresponds to that vector. Well, this one is plus 5 for every 1. And so this is the two parts of it. And what we expect is that when we play it, watch this. The vector just follows right along. Let me back that up here. Maybe I'll go nice and slow here, right? You notice all that's happening is this vector stays put because its eigenvalue is 1. So you just stay that amount in that direction. And meanwhile, this one shortens to only 40% of what it was last time. Oop. And it just keeps going. And that's it. What if we instead started at being rainy? Well, now, if you start at rainy, you still have the eigenvectors in the same directions as they were because they're eigenvectors. But now you have to add a different component. So now you have a big 1 minus 1 component in this direction here. And now if we run it forward, what's it going to do? This direction is still going to decay at 0.4. Oop, oop, oop. And it converges to the same value of 5, 6, 1, 6, because it has to do that, because that's the direction of the primary eigenvector. Pretty cool. If you want to, we can make this be a little bit more fun. Like, let's say you had a really hectic world where you say that if you start off, now this is kind of the opposite of everything, where if it's sunny today, then there's a 90% chance it's going to be rainy tomorrow. And then if it's rainy today, there's an 80% chance it's going to be sunny. So you just have it constantly just flicking back and forth, oscillating back and forth. Now let's take a look at this. This should look pretty cool too. Here's the eigenvectors. Same thing, right? So, I in here, I actually calculate the eigenvectors and I plot them here. So now it has a different eigenvector. This one looks like approximately 1, 1, and minus 1, 1. But I believe the eigenvalue here, this one's still 1, but I believe this one's going to be negative thereabouts. And this can't be 1, 1 is probably something like, because there has to end up being a slightly better chance of it being rainy because you switch more often to rainy than you switch from rainy to sunny. But here, look at this. It has a negative eigenvalue. So now it oscillates back and forth. But you can see it still stays right along that line. That eigenvector just is still getting smaller with time, right? Let me slow that down a bit. But it stays along that direction. It just flips and gets shorter. Back and forth, back and forth. And that's all it can do. As all these things can do. Pretty cool. All right. So that does it with analyzing just these basic Markov chains. Now let's spend a minute